picture this for a moment. Right now, as you sit listening to these words, the atoms in your body are doing something that would make even the most creative science fiction writer pause in disbelief. They're existing in multiple places simultaneously, tunneling through barriers that should be impossible to cross, and maintaining instantaneous connections with particles scattered across the universe. Your very existence depends on phenomena that completely violate everything your common sense tells you about how reality should work. Welcome to the world of quantum physics, where the rules that govern our everyday experience crumble into dust, and the universe reveals itself to be far stranger, far more mysterious, and far more beautiful than anything our ancestors could have imagined. I'm here to guide you on a journey through the looking glass of modern physics, where we'll explore how the deepest discoveries of science have shattered our most fundamental assumptions about the nature of reality itself. This isn't just an academic exercise. By the time we finish this exploration together, you'll never look at the world around you the same way again. Every solid object will seem a little less solid. Every moment of certainty will carry a whisper of quantum mystery, and every interaction you have with the world will be tinged with the profound recognition that reality is nothing like what it appears to be. Take a deep breath and settle in, because we're about to embark on an intellectual adventure that will challenge everything you thought you knew about existence itself. And trust me, the rabbit hole goes deeper than Alice ever imagined. For thousands of years, human beings have built their understanding of reality on what seems like rock-solid common sense. If you throw a ball, it follows a predictable arc. If you close a door, it stays closed until someone opens it. Objects exist in one place at one time, and they have definite properties whether anyone is looking at them or not. Cause precedes effect. Things can only influence other things they're directly connected to, and the act of simply observing something doesn't change its fundamental nature. These assumptions feel so natural, so obviously true, that questioning them seems almost absurd. After all, they're based on millions of years of evolutionary experience, refined through countless generations of human ancestors who survived by understanding how the physical world behaves. Your brain is literally wired to process reality according to these classical rules, because at the scale of everyday life, they work perfectly. But here's where the story takes its first shocking turn. In the early 20th century, scientists began probing deeper into the fabric of reality than anyone had ever looked before. They expected to find smaller versions of the familiar world we know, tiny building blocks that behaved according to the same logical principles that govern our macroscopic experience. Instead, they discovered something that challenged the very foundations of human knowledge. What they found was a realm where particles exist in multiple states simultaneously, where the act of observation fundamentally changes what is being observed, and where objects separated by vast distances maintain mysterious, instantaneous connections that seem to violate the basic structure of space and time itself. They had stumbled into the quantum world, and nothing would ever be the same. The word quantum comes from the Latin word meaning how much, but it might as well mean how impossible. Because quantum physics describes a reality so foreign to our everyday experience that even the scientists who discovered these phenomena spent decades arguing about what they actually meant. Albert Einstein, one of the greatest minds in human history, famously declared that God does not play dice with the universe, rejecting the fundamental randomness that quantum theory seemed to demand. Yet experiment after experiment confirmed that the universe does indeed appear to be playing dice, and it's playing them according to rules that make no sense from our ordinary perspective. Consider this mind-bending fact that we'll explore in detail. When you fire electrons one at a time through two parallel slits toward a screen, each electron somehow goes through both slits simultaneously and interferes with itself to create a pattern that's only possible if it travelled multiple paths at once. But the moment you try to peek and see which slit the electron actually went through, the entire pattern changes, as if the electron retroactively decided to behave like a normal particle just because you were watching. This isn't science fiction or philosophical speculation. This is measurable, repeatable, experimental fact that has been confirmed thousands of times in laboratories around the world. And it represents just the beginning of quantum physics' assault on common sense. As you listen to these ideas, notice how they might challenge assumptions you carry about the nature of knowledge itself. How do we know what we know? What does it mean for something to exist if its very existence seems to depend on whether we're looking at it? Let's start our deeper dive into this strange new world by examining what happens when we try to apply our everyday logic to the quantum realm. In classical physics, the physics of Newton and everyday experience, objects have definite properties. A ball has a specific location, a definite velocity, and a particular colour, regardless of whether anyone is observing it. These properties exist independently of measurement, waiting to be discovered rather than created by the act of discovery. But quantum mechanics paints a radically different picture. At the quantum level, particles don't have definite properties until they're measured. Instead, they exist in what physicists call superposition states, where they embody all possible values of a property simultaneously. An electron doesn't have a specific location. It exists as a probability cloud spread throughout space, with different regions representing different likelihoods of where it might be found if someone looks for it. This isn't simply a limitation of our measuring instruments or our knowledge. It's a fundamental feature of reality itself. The particle genuinely exists in multiple states at once, and the act of measurement doesn't reveal a pre-existing property, but actually forces the particle to choose one specific state from all the possibilities it was simultaneously embodying. Imagine if this applied to everyday objects. Picture a coin that, when flipped, doesn't land on heads or tails, but exists in a superposition of both states simultaneously until someone looks at it. The coin would be neither heads nor tails, but both heads and tails, existing in a ghostly combination of all possibilities until the moment of observation collapsed this quantum superposition into a definite classical result. This seems absurd because our brains have evolved to process information about objects that exist in definite states. We need to know whether that rustling in the bushes is a predator or just the wind, whether that fruit is ripe or poisonous, whether that cliff edge is stable or crumbling. Survival depends on the ability to extract definite information about definite properties of definite objects. But quantum mechanics suggests that this classical definiteness is actually an illusion that emerges only at larger scales. The mathematics of quantum mechanics, developed over decades by some of the most brilliant minds in human history, describes this strange reality with breathtaking precision. The theory allows scientists to calculate the probabilities of different measurement outcomes with extraordinary accuracy, predicting experimental results to more than 10 decimal places in some cases. Yet despite this mathematical elegance, the physical picture it paints violates our deepest intuitions about how reality should work. Werner Heisenberg, one of the founders of quantum mechanics, captured this tension perfectly when he observed that quantum mechanics is so strange that nobody understands it. Only some people get used to it. Even today, nearly a century after its discovery, physicists continue to debate what quantum mechanics actually tells us about the nature of reality. But the strangeness is just beginning. Let's examine another quantum phenomenon that demolishes our classical assumptions about the nature of matter and energy. Throughout human history, we've categorized things as either waves or particles. Waves, like sound or water ripples, spread out through space and can interfere with each other, creating patterns of reinforcement and cancellation. Particles, like rocks or raindrops, exist at definite locations and follow predictable trajectories through space. This wave-particle distinction seems fundamental to the nature of reality itself. How could something be both a wave and a particle? It would be like asking whether music is a melody or a rhythm. The categories seem mutually exclusive, representing completely different ways of existing in the physical world. Yet quantum mechanics reveals that this classical distinction is another illusion. Light, which we experience as waves creating interference patterns and diffraction effects, also behaves like a stream of particles called photons when we measure it in certain ways. Electrons, which we typically think of as tiny particles orbiting atomic nuclei, also exhibit wave-like behavior, creating interference patterns just like light waves do. This isn't a case of sometimes acting like a wave and sometimes like a particle. Quantum objects simultaneously possess both wave and particle properties, manifesting one aspect or the other depending on how we choose to observe them. The choice of measurement determines which face of reality we see, as if the universe is a shapeshifter that transforms itself based on the type of question we ask. The famous double-slit experiment, which we'll explore in exquisite detail, demonstrates this wave-particle duality in the most direct and disturbing way possible. When particles are fired one at a time through two parallel slits, they create an interference pattern that's only possible if each individual particle somehow went through both slits simultaneously, like a wave. But when we place detectors at the slits to see which path each particle actually takes, the interference pattern vanishes, and the particles behave like classical objects going through one slit or the other. The implications are staggering. The experiment suggests that the particle's path doesn't exist as a definite fact until we measure it. The act of measurement doesn't simply reveal which slit the particle went through, it actually determines which slit it went through. Reality at the quantum level appears to be fundamentally observer-dependent, shaped by the very act of observation in ways that classical physics never imagined possible. As you contemplate this, take a moment to consider how this might relate to your own experience of reality. How much of what you perceive as fixed and definite might actually be more fluid than it appears? This observer dependence leads us to one of the most profound and unsettling aspects of quantum mechanics, the measurement problem. In classical physics, measurement is straightforward. You point an instrument at an object, and the instrument reveals the object's pre-existing properties without fundamentally changing them. You might disturb the object slightly through the act of measurement, but its essential properties exist independently of your investigation. Quantum mechanics turns this comfortable assumption upside down. According to the mathematical formalism of quantum theory, unmeasured quantum systems evolve according to the Schrödinger equation, which describes how probability waves change over time. These waves can exist in superposition states, embodying multiple contradictory properties simultaneously. But the moment a measurement is performed, something dramatic happens that the Schrödinger equation cannot describe. The wave function collapses, and the system instantly transitions from existing in multiple states to existing in one definite state. This collapse process is instantaneous and discontinuous, completely unlike anything else in physics. It's as if the universe suddenly snaps from a condition of pure possibility into a condition of definite actuality, triggered by the simple act of looking. But what exactly constitutes a measurement? Does it require a conscious observer, or can an unconscious detector trigger the collapse? Does the collapse happen when the particle interacts with the measuring device, when the device records the result, when a human reads the result, or at some other point in the process? These questions have puzzled physicists for decades because they strike at the heart of the relationship between consciousness and physical reality. Some interpretations of quantum mechanics suggest that consciousness plays a fundamental role in collapsing wave functions and determining the nature of reality. Others propose that the collapse is an objective physical process that occurs whenever quantum systems interact with their environment in certain ways, regardless of whether any conscious observer is present. The measurement problem reveals how quantum mechanics challenges not just our understanding of matter and energy, but our understanding of knowledge itself. What does it mean to know something about the world if the act of knowing changes what we're trying to know? How can we maintain the scientific ideal of objective observation when observation itself appears to be a creative rather than merely a revealing act? These questions become even more perplexing when we consider quantum entanglement, perhaps the most mysterious phenomenon in all of physics. When two particles become entangled, they lose their individual identities and become part of a single quantum system, even when separated by vast distances. Measuring one particle instantly affects the other, regardless of how far apart they are, in a way that seems to violate the fundamental principle that nothing can travel faster than light. Einstein famously called this spooky action at a distance, and he refused to believe that nature could work in such a seemingly impossible way. He proposed that quantum mechanics must be incomplete, that there must be hidden variables determining the behavior of entangled particles in ways that preserve the classical notions of locality and realism. But decades of increasingly sophisticated experiments have confirmed that entanglement is real, and that Einstein's hidden variable theories cannot explain the observed correlations between entangled particles. The implications are profound. Entanglement suggests that the universe is not composed of separate objects interacting through local forces, but rather forms an interconnected web where events in one location can instantaneously influence events anywhere else. The classical picture of reality as a collection of independent objects existing in separate locations breaks down at the quantum level, replaced by a more holistic view where the whole system has properties that cannot be reduced to the properties of its individual parts. This interconnectedness operates according to principles that seem to transcend our ordinary concepts of space and time. When Alice measures her entangled particle in New York, Bob's corresponding particle in Tokyo instantly knows about Alice's measurement and adjusts its behavior accordingly. This correlation occurs faster than light could travel between the two locations, suggesting that entangled particles share a connection that exists outside the normal structure of space-time. Yet despite this apparent faster-than-light correlation, no information can actually be transmitted through entanglement. Bob cannot use his measurements to decode any message that Alice might be trying to send. The correlation is real and instantaneous, but it cannot be exploited for communication. It's as if the universe allows for non-local connections, while still preserving the causal structure that prevents paradoxes from arising. As we delve deeper into these quantum mysteries, we begin to see how they form a coherent picture of reality that's radically different from our everyday experience. The classical world of definite objects with definite properties existing in definite locations gives way to a quantum world of possibilities, correlations, and observer-dependent realities that challenges our most basic assumptions about the nature of existence itself. In our next exploration, we'll dive even deeper into the specific experiments that revealed these quantum phenomena, examining exactly how scientists discovered that reality behaves in ways that seem to violate the laws of logic itself. We'll see how the simple act of firing particles through two slits opened a window into a universe stranger than any science fiction writer ever imagined, and we'll explore what this might mean for our understanding of consciousness, free will, and the very nature of existence. But for now, let these ideas settle gently into your awareness. Notice how they feel in your mind. Do they create a sense of wonder, confusion, or perhaps both? As you move through your day, you might find yourself looking at familiar objects with slightly different eyes, wondering about the quantum dance of possibilities that underlies their apparent solidity. This is just the beginning of a journey that will transform how you see everything around you. The moment you begin to truly understand what quantum tunneling means, the solid ground beneath your feet starts to feel a little less certain. Right now, the electrons in your body are performing what can only be described as magic tricks, slipping through energy barriers that classical physics insists should be impossible to cross. They're not breaking the rules of reality, they're revealing that the rules we thought we knew were never the whole story. This phenomenon, discovered in the depths of quantum mechanics, shows us that particles can pass through walls, barriers, and obstacles without ever having enough energy to climb over them. It's as if you could walk through a brick wall not by breaking it down or finding a door, but by somehow existing on both sides of the wall simultaneously, until you decide which side you prefer to be on. Quantum tunneling operates according to principles that make our everyday experience seem like a carefully constructed illusion. In the classical world, if you roll a ball toward a hill, the ball either has enough energy to reach the top and continue down the other side, or it doesn't, in which case it rolls back toward you. The mathematics are straightforward, the outcome is predictable, and common sense remains intact. But in the quantum realm, particles approaching energy barriers behave according to entirely different rules. Even when a particle lacks the energy to classically surmount a barrier, quantum mechanics reveals that there's always a probability, sometimes small but never zero, that the particle will appear on the other side. The particle doesn't climb over the barrier or tunnel through it in any mechanical sense. Instead, its probability wave extends beyond the barrier, creating a finite chance that a measurement will find the particle in a location where classical physics says it cannot exist. This isn't theoretical speculation. Quantum tunneling is the foundation of technologies you use every day. The scanning tunneling microscope, which can image individual atoms, works by measuring the current created when electrons tunnel through the vacuum between a sharp metal tip and a surface. Flash memory drives store information by trapping electrons in quantum wells, relying on tunneling effects to write and erase data. Even the nuclear fusion reactions that power the sun depend on quantum tunneling, as protons tunnel through the electromagnetic barriers that would otherwise prevent them from fusing together. Think about this for a moment. The light streaming from the sun, the warmth on your skin, the very energy that sustains all life on Earth, exists because particles deep in the solar core are continuously performing quantum magic tricks that violate our classical intuitions about how matter should behave. Every photon that reaches your eyes carries with it the signature of quantum impossibility made manifest. The mathematics describing tunneling reveals something profound about the nature of probability itself. In classical mechanics, probabilities reflect our ignorance about the exact state of a system. We flip a coin and assign a 50% probability to heads, not because the coin is genuinely random, but because we don't know enough about its initial velocity, spin rate, and air resistance to predict the outcome with certainty. Given perfect information about all relevant variables, classical systems are perfectly predictable. Quantum tunneling operates according to a fundamentally different kind of probability. The probability that a particle will tunnel through a barrier isn't a measure of our ignorance about hidden variables determining its path. It's an intrinsic property of the particle's wave function, built into the fabric of reality itself. The particle doesn't have a predetermined fate waiting to be revealed by measurement. Instead, it exists in a superposition of being on both sides of the barrier simultaneously, until the moment of observation forces it to choose one side or the other. This quantum probability has a strange, almost magical quality. Unlike classical probability, which simply describes our uncertainty about definite facts, quantum probability seems to describe the actual creation of facts through the process of measurement. The particle doesn't tunnel or fail to tunnel and then wait for us to discover which occurred. The act of measurement appears to participate in determining which outcome becomes real. As you contemplate these ideas, notice how they might shift your perception of possibility itself. What barriers in your own experience might be less absolute than they appear? The phenomenon becomes even stranger when we consider its implications for the nature of identity and persistence. When a particle tunnels through a barrier, what exactly travels from one side to the other? In classical physics, this question has an obvious answer. The particle itself, a discrete object with definite properties, moves from location A to location B. But quantum tunneling reveals that this classical picture is fundamentally inadequate. The particle doesn't exist as a localized object during the tunneling process. Instead, its wave function spreads out across space, existing partially on both sides of the barrier simultaneously. The particle's identity becomes distributed, smeared across regions of space-time in ways that challenge our most basic notions of what it means for something to exist in a particular place at a particular time. When measurement finally occurs and the particle is found on one side of the barrier or the other, the wave function collapses and the particle's identity consolidates into a definite location. But the process by which this consolidation occurs remains one of the deepest mysteries in quantum mechanics. How does the distributed quantum identity transform into the localized classical object that we ultimately observe? Different interpretations of quantum mechanics offer different answers to this question, but none of them preserve our classical intuitions about the nature of objects and their properties. Some suggest that all possible outcomes occur simultaneously in parallel universes, with our measurements simply selecting which universe we experience. Others propose that consciousness plays a fundamental role in collapsing the wave function and determining which outcome becomes real. Still others argue that the collapse is an objective physical process that occurs whenever quantum systems interact with their environment in sufficiently complex ways. What all these interpretations share is a recognition that quantum tunneling reveals something profound about the relationship between possibility and actuality. The classical world appears to be constructed from definite facts, but the quantum world suggests that these facts emerge from a deeper realm of pure possibility, where contradictory states can coexist until the moment when observation forces a choice between them. This leads us to another quantum phenomenon that challenges our understanding of identity and separateness in even more dramatic ways. Werner Heisenberg's uncertainty principle reveals that the very concept of a particle having definite properties independent of measurement is fundamentally flawed. According to this principle, certain pairs of properties, such as position and momentum, cannot be simultaneously determined with perfect precision, no matter how sophisticated our measuring instruments become. This isn't a technological limitation that better equipment might eventually overcome. It's a fundamental feature of quantum reality, built into the mathematical structure of the theory itself. The uncertainty doesn't arise from clumsy measurements that disturb the system being studied. It emerges from the wave-like nature of matter itself. To understand why this is so revolutionary, imagine trying to measure both the position and momentum of a classical particle, like a marble rolling across a table. In principle, there's no fundamental limit to how precisely these properties can be determined. With sufficiently sensitive instruments, you could measure the marble's location to within a fraction of an atomic diameter and its velocity to within an infinitesimal margin of error. The precision of your measurements would be limited only by the quality of your instruments and the care with which you conducted the experiment. But quantum particles don't behave like classical marbles. They exist as probability waves spread out through space, and these waves have a peculiar property. The more precisely you try to localize the wave in space, the more spread out it becomes in momentum, and vice versa. It's as if the universe enforces a cosmic trade-off, allowing you to know one aspect of the particle state precisely only at the cost of increased uncertainty about complementary aspects. This trade-off isn't arbitrary or accidental. It reflects something deep about the nature of information itself in quantum systems. The wave function that describes a quantum particle contains a finite amount of information, and this information can be distributed across different properties in various ways, but the total amount available is fundamentally limited. Gaining precise information about position necessarily means losing precise information about momentum, not because of any measurement disturbance, but because of the inherent structure of quantum reality. The philosophical implications are staggering. If particles don't have definite positions and momenta simultaneously, what does this tell us about the nature of physical objects? Are electrons and photons actually objects in any meaningful sense, or are they something more abstract, patterns of possibility that occasionally crystallize into definite properties when we insist on measuring them? Heisenberg himself struggled with these questions, ultimately concluding that quantum mechanics forces us to abandon the classical notion of objective reality existing independently of observation. In his view, the uncertainty principle reveals that nature doesn't consist of things, but rather of relationships and correlations that emerge through the process of measurement. This shift from thinking about things to thinking about relationships becomes even more apparent when we examine quantum entanglement in detail. When two particles become entangled, they don't simply form a system where each particle influences the other. Instead, they lose their individual identities entirely, becoming parts of a single, non-separable quantum whole. Imagine two coins that have been entangled in some quantum sense. In the classical world, each coin would have its own definite state, heads or tails, regardless of what happens to the other coin. You might not know which state each coin is in until you look, but each coin would have a definite state waiting to be discovered. Entangled quantum coins behave entirely differently. Rather than each coin having its own state, the two-coin system exists in a superposition where the coins are correlated in ways that transcend classical logic. The system might be in a state where both coins will always show the same results when measured, or always show opposite results, but neither coin has an individual state until a measurement is performed. When Alice measures her entangled coin in New York and finds heads, she instantly knows that Bob's coin in Tokyo will show a specific result when he measures it, either heads or tails depending on the type of entanglement. This correlation occurs instantaneously, regardless of the distance separating the coins, in apparent violation of Einstein's principle that nothing can travel faster than light. But here's the truly mysterious part. The correlation isn't explained by the coins sending signals to each other, or by some hidden mechanism that coordinates their behavior. Instead, the entangled system exists as a single, indivisible whole until the moment when measurement forces it to divide into separate parts with definite properties. Einstein found this idea so disturbing that he spent the later years of his life trying to prove that quantum mechanics must be incomplete. He believed that entangled particles must have hidden properties determined in advance that account for their correlated behavior without requiring any instantaneous influence between distant locations. These hidden variable theories seem necessary to preserve the classical notions of locality and realism that form the foundation of his worldview. But in 1964, physicist John Bell devised a mathematical test that could distinguish between Einstein's hidden variable theories and the predictions of quantum mechanics. When experiments were finally performed in the 1970s and 1980s, they decisively confirmed the quantum predictions and ruled out local hidden variable theories. The implications are profound. Either the world is fundamentally non-local, with entangled particles maintaining instantaneous connections across arbitrary distances, or it's not realistic in the classical sense, with particles lacking definite properties independent of measurement. Either conclusion represents a radical departure from our ordinary understanding of reality. Most physicists have accepted that quantum entanglement reveals genuine non-locality in nature, but this non-locality operates according to subtle rules that prevent it from being used for faster-than-light communication. Alice cannot use her measurements to send a message to Bob, because the results of her measurements appear random from her perspective. The correlation becomes apparent only when Alice and Bob compare their measurement results afterward, using classical communication channels that respect the speed of light limit. This creates a picture of reality where the universe is fundamentally interconnected at the quantum level, with correlations that transcend space and time. Yet these correlations remain hidden from individual observers until they choose to compare notes. It's as if the universe maintains a deeper unity that manifests through relationships rather than through the properties of separate objects. As you reflect on these ideas, consider how they might influence your understanding of separation and connection in your own experience. If the fundamental particles that compose your body are governed by principles that emphasize relationship over individuality, what might this suggest about the nature of identity itself? The strange world of quantum mechanics becomes even more puzzling when we examine how these microscopic phenomena relate to the macroscopic world we experience directly. Why don't we see superposition states, tunneling effects, or entanglement correlations in our everyday lives? If electrons can exist in multiple locations simultaneously, why can't automobiles? If particles can tunnel through barriers, why can't we walk through walls? The answer lies in a process called decoherence, which describes how quantum systems lose their quantum properties when they interact with their environment. Quantum superposition states are extremely fragile, easily disrupted by any interaction with surrounding particles, fields, or radiation. For microscopic systems that can be isolated from their environment, quantum effects can persist long enough to be observed and measured. But for macroscopic objects, which constantly interact with countless environmental influences, quantum coherence is destroyed almost instantaneously. Think of a quantum superposition as being like a perfectly balanced pencil standing on its point. In principle, the pencil could remain balanced indefinitely, but in practice, the slightest vibration, air current, or disturbance will cause it to topple over. Similarly, quantum superposition states can exist in principle for objects of any size, but in practice, larger objects interact so strongly with their environment that their quantum coherence collapses immediately. This explains why the quantum world seems so foreign to our everyday experience. We evolved in an environment where quantum effects are almost always masked by decoherence, leaving us with brains that are exquisitely adapted to processing information about classical objects with definite properties. Our perceptual and cognitive systems are optimized for tracking things that exist in specific locations, move along definite trajectories, and maintain their identities over time. But the classical world we perceive is actually an emergent phenomenon arising from underlying quantum processes. The apparently solid chair you're sitting on is composed of atoms whose electrons exist in probability clouds, held together by electromagnetic forces that operate according to quantum principles. The classical properties of the chair, its definite shape, location, and material characteristics, emerge from the collective behavior of countless quantum particles whose individual properties remain fundamentally uncertain. This emergence of classical behavior from quantum foundations is one of the most active areas of research in modern physics. Scientists are working to understand exactly how and when quantum systems transition to classical behavior, and whether this transition is gradual or sudden, objective or observer dependent. Some researchers are even exploring whether quantum effects might persist at larger scales under special circumstances. They're investigating whether biological systems might exploit quantum coherence for enhanced efficiency in processes like photosynthesis or avian navigation. Others are working to create artificial quantum systems that can maintain coherence at macroscopic scales, potentially leading to revolutionary technologies like quantum computers and quantum communication networks. If you enjoy drifting through these explorations without interruption, members get every episode 48 hours early, completely ad-free. You can join them whenever you feel ready. These investigations are revealing that the boundary between quantum and classical behavior isn't as sharp as once thought. Rather than representing completely separate realms, the quantum and classical worlds appear to be different aspects of a more fundamental reality that transcends both descriptions. This brings us to one of the most profound questions raised by quantum mechanics. What role, if any, does consciousness play in the transition from quantum possibilities to classical realities? Some interpretations of quantum mechanics suggest that consciousness is necessary to collapse wave functions and determine which outcomes become real. Others argue that consciousness is simply another physical process that operates according to quantum principles. With no special status in determining the nature of reality, the relationship between consciousness and quantum mechanics remains one of the most controversial and fascinating frontiers in modern science. While most physicists are skeptical of claims that consciousness directly influences quantum events, the measurement problem in quantum mechanics does raise profound questions about the nature of observation, information, and reality itself. What we can say with confidence is that quantum mechanics has revealed a universe far stranger and more mysterious than our ancestors ever imagined. The solid, predictable world of everyday experience emerges from a quantum foundation that seems to violate our deepest intuitions about logic, causality, and the nature of existence itself. As we continue our journey through the quantum realm, we'll explore how these discoveries are reshaping not just our understanding of physics, but our understanding of reality, consciousness, and our place in the cosmic order. The implications extend far beyond the laboratory, touching on fundamental questions about the nature of knowledge, identity, and the relationship between mind and matter. But for now, let these quantum mysteries settle gently into your awareness. Notice how they challenge your assumptions about solidity, separateness, and certainty. As you move through your day, you might find yourself wondering about the quantum dance of possibilities that underlies every apparently solid surface, every moment of apparent certainty, every experience of apparent separation from the world around you. The journey into quantum reality is just beginning, and the deeper we go, the more we discover that reality itself is far more fluid, interconnected, and mysterious than we ever dared to imagine. The moment scientists first observed what happens when you try to watch a quantum particle make a decision, they discovered something that would haunt physics for the next century. The particle, as if aware it was being observed, completely changed its behaviour, not gradually, not partially, but instantly and completely, as if reality itself was putting on a performance whenever someone was looking. This is where our exploration of quantum mechanics takes its most unsettling turn, into a realm where the very act of gaining knowledge appears to reshape the nature of what we're trying to know. We're about to examine the most famous experiment in quantum physics, one so simple a child could understand the setup, yet so profound in its implications that it continues to challenge our most basic assumptions about the relationship between consciousness and reality. Picture a wall with two narrow slits cut into it, like doorways side by side. Behind this wall sits a screen that can detect where particles land, much like how a movie screen shows where light hits it. The experiment seems almost trivially simple. Fire particles one at a time toward the two slits and observe where they land on the screen behind. If particles behaved like tiny marbles, as our classical intuition suggests they should, you'd expect to see two bright strips on the screen directly behind each slit, with most particles landing in those areas and fewer scattered around the edges. This is exactly what happens when you fire actual marbles or bullets through two openings. Each projectile goes through one slit or the other, and the pattern on the back wall reflects this straightforward either-or logic. But quantum particles refuse to cooperate with our expectations. When electrons or photons are fired one at a time through the double slits, they create something extraordinary, an interference pattern of alternating bright and dark bands across the entire screen. This striped pattern is the unmistakable signature of waves, not particles. It's as if each individual particle somehow went through both slits simultaneously, interfered with itself, and created the complex pattern that emerges only when waves from different sources meet and either reinforce or cancel each other. Let that sink in for a moment. A single particle fired alone through the apparatus, creates a pattern that should be impossible unless that one particle existed in multiple places at once. The particle appears to be taking every possible path through the experimental setup, exploring all available routes simultaneously, then somehow combining all these possibilities into a single point of impact on the detection screen. This wave-like behavior persists even when particles are fired so slowly that only one exists in the apparatus at any given moment. Over time, as hundreds or thousands of individual particles hit the screen one by one, the interference pattern gradually builds up, dot by dot. Each particle contributes a single point of light, yet collectively they form the striped pattern that reveals the wave nature underlying their seemingly particle-like arrivals. The implications challenge our deepest intuitions about the nature of individual identity. If a single electron creates an interference pattern, it must somehow be interfering with itself. This suggests that the electron doesn't follow a single path through the experiment, but instead exists in a superposition of all possible paths simultaneously. The particle is neither fully here nor fully there, but distributed across space in a way that defies our ordinary concepts of location and identity. But the experiment's most disturbing revelation comes when scientists decided to peek behind the curtain and determine which slit each particle actually passes through. They placed detectors at each slit, devices that could register the passage of particles without significantly disturbing their motion. Surely, they reasoned, this would settle the question once and for all by revealing the particle's actual path while preserving the wave-like interference pattern. The results shattered their expectations. The moment the detectors were activated, the interference pattern vanished completely. Instead of the complex striped pattern that had appeared when no one was watching, the screen now showed exactly what classical intuition predicted. Two bright bands directly behind the slits, as if the particles had suddenly remembered how to behave like proper classical objects. The particles hadn't been damaged or significantly disturbed by the detection process. The detectors were designed to be as gentle as possible, registering the passage of particles through methods that barely interacted with them. Yet somehow, the mere possibility of gaining information about which path each particle took was enough to fundamentally alter the nature of the experiment's outcome. Turn the detectors off, and the wave-like interference pattern returns. Turn them on, and the pattern disappears, replaced by classical particle behavior. The transition is immediate and complete, as if reality itself switches between two entirely different modes of existence based solely on whether information about the particle's path is available in principle. As you contemplate this strange behavior, notice how it might reflect something profound about the relationship between knowledge and reality in your own experience. When you observe your own thoughts and emotions closely, do they behave differently than when they arise unobserved? This isn't simply a matter of the detection process physically disturbing the particles. The effect occurs even with the most sophisticated detection methods that barely interact with the particles at all. Instead, it appears that the universe fundamentally distinguishes between situations where path information could be obtained and situations where it cannot, regardless of whether anyone actually bothers to look at the detector readings. Some interpretations of this result suggest that the particle somehow knows whether it's being watched and adjusts its behavior accordingly. Others propose that the act of measurement creates the very property it attempts to measure, rather than simply revealing a pre-existing characteristic. Still others argue that consciousness plays a direct role in collapsing the wave function and determining which version of reality manifests. The philosophical implications extend far beyond physics into questions about the nature of knowledge itself. If the act of gaining information about a system fundamentally changes that system, what does this tell us about the relationship between observer and observed? Can we ever truly study anything without participating in its creation? These questions become even more profound when we consider what happens in variations of the double-slit experiment that probe the boundaries between measurement and reality. In one particularly mind-bending version, researchers set up the experiment so that they could choose whether to measure the particle's path after it had already passed through the slits, but before it hit the detection screen. According to classical logic, this shouldn't matter. The particle should have already decided whether to behave like a wave or a particle by the time it passed through the slits. The choice of whether to measure its path afterward shouldn't be able to retroactively influence behaviour that had already occurred. But quantum mechanics doesn't respect our classical notions of temporal causality. In these delayed choice experiments, the decision of whether to measure the particle's path, made after the particle has passed through the slits, still determines whether an interference pattern appears on the screen. It's as if the particle's past behaviour depends on future decisions about what information will be extracted from the experiment. This suggests that the quantum world operates according to principles that transcend our ordinary understanding of cause and effect. The particle doesn't simply follow a predetermined path that we either reveal or fail to reveal through measurement. Instead, the act of measurement appears to participate in determining what path the particle took, even when that determination occurs after the relevant events have supposedly already happened. The implications for our understanding of time and causality are staggering. If quantum events can be influenced by future measurements, then the arrow of time that seems so fundamental to our experience might be less absolute than we imagine. Past, present, and future might be more intertwined at the quantum level, with events in one temporal location influencing events in others in ways that violate our classical expectations. These temporal puzzles lead us deeper into the mystery of quantum measurement and its relationship to consciousness and reality. Some physicists have proposed that consciousness plays a special role in collapsing wave functions, because conscious observers are the only entities capable of processing information in ways that create definite outcomes from quantum possibilities. According to this view, the quantum world exists in a state of pure potential until consciousness engages with it through the act of observation. The wave function describes not what is, but what could be, and consciousness serves as the mechanism by which possibility transforms into actuality. The universe in this interpretation is fundamentally participatory, requiring conscious observers to complete the transition from quantum potential to classical reality. Other interpretations reject this special role for consciousness, arguing that any complex physical system capable of recording information can trigger wave function collapse. In this view, consciousness is simply another physical process subject to the same quantum laws as everything else, with no unique power to determine the nature of reality. But even these more materialistic interpretations struggle to explain exactly what constitutes a measurement and why the mere possibility of gaining information appears to be sufficient to alter quantum behaviour. The measurement problem remains one of the most profound unsolved puzzles in physics, touching on fundamental questions about the nature of information, causality, and reality itself. The debate over interpretation has practical consequences for our understanding of quantum technologies and their potential applications. If consciousness does play a special role in quantum measurement, then quantum computers and other quantum devices might behave differently when humans are directly involved in their operation versus when they run autonomously. Some researchers are exploring whether human intention or attention might influence quantum random number generators or other quantum systems in measurable ways. While most of these studies remain controversial and their results are disputed, they represent serious attempts to test whether consciousness has any direct influence on quantum events. The scientific consensus remains that individual thoughts or intentions do not directly control quantum systems in ways that could be used to manifest desired outcomes or influence reality at macroscopic scales. The quantum effects that consciousness might potentially influence, if any, would likely be extremely subtle and confined to very specific experimental conditions. However, the deeper question of how consciousness relates to the quantum mechanical description of reality remains open. Even if consciousness doesn't directly control quantum events, the fact that conscious observation appears to play a role in the transition from quantum possibilities to classical realities suggests a profound connection between mind and the fundamental structure of the universe. This connection becomes even more intriguing when we consider the role of information in quantum mechanics. The double-slit experiment reveals that the availability of which path information, regardless of whether anyone actually accesses it, determines whether particles behave like waves or particles. This suggests that information itself might be a more fundamental aspect of reality than matter or energy. Some physicists have proposed that the universe is fundamentally informational in nature, with matter and energy being emergent properties of underlying informational processes. In this view, consciousness might be the universe's way of processing information about itself, and the act of conscious observation might represent a fundamental type of information processing that plays a special role in determining the nature of reality. The implications extend beyond physics into questions about the nature of mind and its place in the cosmic order. If consciousness is fundamentally connected to the information processing that underlies physical reality, then the emergence of consciousness in the universe might not be an accidental byproduct of complex chemical processes, but rather an inevitable consequence of the universe's informational nature. As you reflect on these ideas, consider how they might influence your understanding of your own consciousness and its relationship to the world around you. If the act of conscious observation plays a role in determining the nature of reality, what might this suggest about the power and responsibility that comes with awareness itself? The mysteries of quantum measurement lead us naturally to consider another phenomenon that challenges our understanding of identity and separateness: quantum entanglement. While the double-slit experiment reveals how individual particles can exist in superposition, states that transcend classical logic, entanglement shows us how multiple particles can lose their individual identities and become part of non-separable wholes that maintain mysterious connections across arbitrary distances. When two particles become entangled, they don't simply influence each other in the way that classical objects do, through forces and fields. Instead, they become part of a single quantum system that cannot be described in terms of the individual properties of its constituent particles. The entangled system has properties as a whole that cannot be reduced to the sum of its parts, violating one of our most fundamental assumptions about the relationship between wholes and their components. Imagine two coins that have become quantum entangled in a particular way. In the classical world, Each coin would have its own definite state, heads or tails, and the state of one coin would have no bearing on the state of the other, unless some physical force connected them. You might not know which state each coin is in until you look, but each coin would possess a definite state waiting to be discovered. Entangled quantum coins behave according to entirely different principles. Rather than each coin having its own independent state, the two-coin system exists in a superposition where the coins are correlated in ways that transcend classical possibility. The system might be in a state where both coins will always show the same result when measured, or always show opposite results, but neither coin individually possesses a definite state until a measurement forces the system to choose. When Alice measures her entangled coin in London and finds heads, she instantly knows with complete certainty what result Bob will obtain when he measures his coin in Tokyo. This correlation occurs immediately, regardless of the distance separating the coins, in apparent violation of Einstein's principle that no influence can travel faster than the speed of light. But the correlation isn't mediated by any signal travelling between the coins. Instead, the entangled system exists as a single, indivisible whole until the moment when measurement forces it to divide into separate parts with definite properties. The coins don't communicate with each other. They share an identity that transcends spatial separation until measurement compels them to develop individual identities. Einstein found this idea so disturbing that he devoted considerable effort to proving it couldn't be correct. Along with colleagues Boris Podolsky and Nathan Rosen, he argued that quantum mechanics must be incomplete, that entangled particles must possess hidden properties determined in advance that account for their correlated behaviour without requiring any instantaneous influence between distant locations. These hidden variable theories seem necessary to preserve the classical notions of locality and realism that form the foundation of Einstein's worldview. Locality holds that objects can only be directly influenced by their immediate surroundings, while realism maintains that objects possess definite properties independent of observation. Einstein believed that any complete theory of physics must respect both principles. But in the 1960s, physicist John Bell devised a mathematical test that could distinguish between Einstein's hidden variable theories and the predictions of quantum mechanics. Bell's theorem showed that any theory based on local hidden variables must satisfy certain mathematical relationships, known as Bell inequalities, in the correlations between entangled particles. When experiments were finally performed in the 1970s and 1980s using increasingly sophisticated techniques, they consistently violated Bell's inequalities in exactly the ways predicted by quantum mechanics. These results definitively ruled out local hidden variable theories and confirm that quantum entanglement represents genuine non-locality in nature. The implications are profound. The experimental violation of Bell's inequalities proves that we must abandon either locality or realism, two principles that seem essential to our ordinary understanding of the world. Either entangled particles maintain instantaneous connections across arbitrary distances, violating locality, or particles lack definite properties, independent of measurement, violating realism. Most physicists have accepted that quantum mechanics reveals genuine non-locality in nature, but this non-locality operates according to subtle rules that prevent it from being exploited for faster-than-light communication. Alice cannot use her entangled particle to send a message to Bob because the results of her measurements appear random from her perspective. The correlation becomes apparent only when Alice and Bob compare their measurement results afterward, using classical communication channels that respect the speed of light limits. This creates a picture of reality where the universe maintains deep interconnections that transcend space and time, yet these connections remain hidden from individual observers until they choose to compare their experiences. It's as if the universe preserves a fundamental unity at the quantum level while still maintaining the causal structure necessary to prevent paradoxes from arising. The non-local correlations revealed by entanglement experiments suggest that the classical picture of reality as a collection of separate objects interacting through local forces is fundamentally inadequate. Instead, the universe appears to be an interconnected web where events in one location can instantaneously influence events anywhere else, though these influences operate according to principles that prevent them from being used for practical communication or control. Take a moment to consider how this might relate to your own sense of connection and separation. If the fundamental particles that compose your body are governed by principles that emphasize relationship over individuality, what might this suggest about the nature of your own identity and its relationship to the broader world? The mystery deepens when we consider that entanglement isn't limited to just two particles. Quantum systems can become entangled in complex networks, where the properties of multiple particles are correlated in ways that cannot be explained by any combination of classical connections. These multi-particle entangled states exhibit even stranger properties than simple two-particle systems, with correlations that seem to violate increasingly fundamental assumptions about the nature of reality. Some of these multi-particle entangled states exhibit properties that have no classical analogue whatsoever. They represent genuinely new forms of organization that emerge only at the quantum level, suggesting that the quantum world contains types of structure and relationship that are completely foreign to our everyday experience. Researchers are now exploring whether biological systems might exploit quantum entanglement for enhanced functionality. Some studies suggest that certain biological processes, such as photosynthesis in plants or navigation in migratory birds, might operate with quantum mechanical efficiency that would be impossible using purely classical mechanisms. While these investigations remain preliminary and their results are still being debated, they raise intriguing possibilities about the role of quantum effects in living systems. If biological evolution has learned to harness quantum entanglement for enhanced survival advantages, it might suggest that consciousness itself could be intimately connected to quantum processes in ways we don't yet understand. The relationship between consciousness and quantum entanglement remains highly speculative, with no scientific consensus about whether conscious states can become entangled or whether consciousness plays any special role in entanglement phenomena. However, the non-local correlations revealed by entanglement experiments do suggest that the universe is far more interconnected than our classical intuitions would suggest. Some interpretations of quantum mechanics propose that consciousness might be fundamentally non-local, capable of accessing information from entangled systems in ways that transcend classical spatial limitations. While these ideas remain unproven and controversial, they point toward possibilities for understanding consciousness that go beyond conventional materialistic frameworks. The practical applications of quantum entanglement are already beginning to transform technology. Quantum communication systems use entangled particles to create communication channels that are fundamentally secure, since any attempt to intercept the quantum information necessarily disturbs the entangled state in detectable ways. quantum computers exploit entanglement to perform certain types of calculations exponentially faster than classical computers, though these devices remain in early stages of development. As these technologies mature, they may provide new ways to test the boundaries between quantum and classical behaviour, potentially revealing whether consciousness has any special relationship to quantum information processing. The development of quantum artificial intelligence systems might eventually shed light on whether consciousness requires quantum processes or whether it can emerge from purely classical computation. But regardless of how these technological developments unfold, the discovery of quantum entanglement has already fundamentally altered our understanding of the nature of reality itself. The universe revealed by quantum mechanics is not a collection of separate objects interacting through local forces, but rather an interconnected web of relationships that transcend our ordinary concepts of space, time, and individual identity. This interconnectedness operates at the deepest level of physical reality, underlying all the apparently separate objects and events of our everyday experience. The classical world of distinct entities with definite properties emerges from a quantum foundation where identity, location, and even existence itself are fluid and context-dependent. As we continue our exploration of quantum reality, we'll delve even deeper into these mysteries, examining how quantum principles might relate to consciousness, free will, and the ultimate nature of existence itself. The journey we've begun leads us into territory where physics, philosophy, and perhaps even spirituality converge in ways that challenge our most fundamental assumptions about the nature of reality and our place within it. But for now, let these quantum mysteries settle gently into your awareness. Notice how they challenge your assumptions about separateness, locality, and the independence of objects from observation. As you move through your world, you might find yourself wondering about the hidden quantum connections that might link you to distant events, the observer effects that your consciousness might be creating, and the deeper unity that might underlie the apparent diversity of your experience. The exploration of quantum reality is revealing a universe far stranger and more interconnected than our ancestors ever imagined, and we've only just begun to glimpse its deepest mysteries. If you enjoy drifting through these explorations without interruption, members get every episode 48 hours early, completely ad-free. You can join them whenever you feel ready. As we venture deeper into the quantum realm, we encounter phenomena that seem to mock the very foundations of logical thought. Here, in the spaces between atoms, reality operates according to principles so alien to our everyday experience that they transform the most basic questions about existence into profound mysteries. What we're about to explore will challenge not just your understanding of physics, but your understanding of what it means for anything to be real at all. The story begins with a puzzle that has tormented physicists for nearly a century, a riddle so fundamental that it strikes at the heart of existence itself. It's called the measurement problem, and it reveals something deeply unsettling about the relationship between possibility and actuality in our universe. Before any measurement occurs, quantum systems don't simply hide their properties from us. They exist in what physicists call superposition states, where contradictory properties are simultaneously real until the moment someone or something demands a definite answer. Imagine holding a coin that refuses to be either heads or tails until you force it to choose by looking at it. But this isn't a matter of the coin secretly being one or the other while you're not looking. According to quantum mechanics, the coin genuinely exists as both heads and tails simultaneously, in a ghostly combination of mutually exclusive states, until observation collapses this superposition into a single, definite reality. This isn't philosophical speculation or mathematical abstraction. It's the foundation of technologies you use every day, from the computer processing these words to the GPS satellite guiding your journey home. Every electron in every circuit exists in superposition until measurement forces it to choose a definite state. And somehow, this fundamental uncertainty at the microscopic level gives rise to the apparent certainty of the macroscopic world you inhabit. The mathematics describing these superposition states reveals something profound about the nature of information itself. The wave function that describes a quantum system contains not just probabilities but something more mysterious. The mathematical structure that allows contradictory possibilities to coexist in a single mathematical entity. It's as if the universe has found a way to be simultaneously consistent and contradictory, logical and paradoxical, definite and indefinite. Consider what this means for your own existence. The atoms composing your body, the neurons firing in your brain as you process these concepts, the photons carrying this information to your eyes, all exist in quantum superposition states until interactions with their environment force them into definite configurations. You are, in a very real sense, a walking, breathing collection of collapsed wave functions, a temporary crystallization of quantum possibilities into classical actuality. But the mystery deepens when we examine what actually causes wave function collapse. Is it the physical interaction with a measuring device? The irreversible recording of information? The involvement of consciousness? Or something else entirely? After nearly a century of investigation, physicists still cannot agree on what constitutes a measurement or why measurement has such a dramatic effect on quantum systems. Some interpretations suggest that consciousness plays a fundamental role in collapsing wave functions, that the universe exists in a state of pure potential until conscious observation forces it to choose definite outcomes from the quantum menu of possibilities. According to this view, consciousness doesn't simply discover reality, but participates in its creation, serving as the mechanism through which the possible becomes actual. Other interpretations propose that wave function collapse is an objective physical process that occurs whenever quantum systems interact with their environment in sufficiently complex ways, regardless of whether any conscious observer is present. In this view, consciousness is simply another physical process subject to quantum laws, with no special power to determine the nature of reality. Still, other interpretations eliminate collapse altogether, suggesting that all possible outcomes of every quantum measurement actually occur simultaneously in parallel universes. When you measure a quantum coin and find heads, there's another version of you in another universe who measures the same coin and finds tails. Every quantum measurement branches the universe into multiple realities, each containing a different version of you experiencing a different outcome. As you contemplate these possibilities, notice how they might shift your understanding of choice and possibility in your own experience. If reality is genuinely created through the act of observation, what responsibility might come with consciousness itself? The implications extend far beyond academic physics into questions about the nature of knowledge, identity, and reality itself. If measurement creates rather than reveals properties, then the classical notion of objective reality existing independently of observation becomes untenable. The universe doesn't consist of things with definite properties waiting to be discovered, but rather of relationships and correlations that crystallize into definite form through the process of interaction and measurement. This relational view of reality represents a radical departure from our ordinary understanding of existence. Instead of thinking about objects with inherent properties, we must learn to think about patterns of correlation that emerge through interaction. The electron doesn't have a definite position and momentum. Instead, it exists as a node in a web of relationships that can manifest different aspects depending on how we choose to interact with it. The philosophical implications ripple outward into every aspect of human knowledge and experience. If the act of knowing changes what we're trying to know, then the scientific ideal of objective observation becomes deeply problematic. We cannot step outside the universe to observe it from a neutral perspective. We are always participants in the reality we're trying to understand, always embedded in the web of relationships that constitute existence itself. This participatory universe reveals itself most dramatically in quantum entanglement experiments, where the measurement of one particle instantly influences its entangled partner, regardless of the distance separating them. The correlation isn't mediated by signals traveling through space, but emerges from the non-separable nature of the entangled system itself. When Alice measures her particle in Paris and finds it spinning clockwise, Bob's particle in Tokyo instantly begins spinning counterclockwise. Not because Alice's measurement sent a signal to Bob's particle, but because the two particles never really separated in the first place. They exist as a single, non-local quantum system that maintains its unity across arbitrary distances until measurement forces it to divide into apparently separate parts. The speed of this correlation has been measured to be at least 10,000 times faster than light, and many physicists believe it occurs instantaneously. This doesn't violate Einstein's speed limit because no usable information travels between the particles. Alice cannot use her measurements to send a message to Bob because her results appear random from her perspective. The correlation becomes apparent only when Alice and Bob compare notes using conventional communication channels. Yet the instantaneous nature of the correlation suggests that space itself might not be as fundamental as we imagine. If entangled particles can maintain perfect correlations across cosmic distances without any time delay, then the spatial separation between them must be in some sense illusory. The universe might be far more interconnected at its foundation than the discrete objects and events of our everyday experience would suggest. Some physicists have proposed that space and time themselves might emerge from more fundamental quantum entanglement relationships. In this view, the familiar three-dimensional space we inhabit is not the stage on which quantum systems perform, but rather an emergent property of the entanglement patterns that connect quantum information across the universe. If space emerges from entanglement, then the apparent separation between objects becomes a kind of useful fiction, a convenient way of organizing information that doesn't reflect the deeper unity underlying all existence. You and the stars, the Earth and the distant galaxies, the thoughts in your mind, and the quantum fields permeating space, all participate in a vast web of correlations that transcends ordinary spatial and temporal relationships. This interconnectedness operates according to principles that challenge our most basic assumptions about identity and independence. Classical objects maintain their identities regardless of their relationships with other objects. A rock remains a rock whether it's sitting alone on a mountaintop or surrounded by other rocks in a stream. Its essential properties exist independently of its context and relationships. But quantum objects lose their individual identities when they become entangled, merging into non-separable wholes that cannot be described in terms of independent parts. An entangled system doesn't consist of separate particles that happen to be correlated. It's a single entity that extends across space and maintains its unity despite apparent spatial separation. This challenges our understanding of what it means to be an individual entity in the first place. If the fundamental constituents of matter don't maintain separate identities, but instead participate in vast networks of quantum correlation, then the boundaries we draw between self and other, between subject and object, between observer and observed, might be more fluid than we imagine. As you reflect on these ideas, consider how they might influence your sense of connection to the world around you. If the particles composing your body are entangled with particles throughout the universe, what might this suggest about the nature of your own identity and its relationship to the broader cosmos? The mystery of quantum identity becomes even more profound when we examine how quantum systems relate to information. In classical physics, information is something that objects possess or convey, like the velocity of a moving particle or the temperature of a heated gas. But quantum mechanics suggests that information might be more fundamental than the objects that appear to carry it. The wave function describing a quantum system is, mathematically speaking, pure information. It doesn't describe physical stuff in the way that classical physics describes matter and energy. Instead, it encodes the probabilities of different measurement outcomes, the correlations between different parts of the system, and the ways that the system can evolve over time. Some physicists have proposed that the universe is fundamentally informational in nature, with matter and energy being emergent properties of underlying informational processes. In this view, the physical world we experience is something like a vast computation, with quantum fields processing information according to the rules of quantum mechanics. If reality is fundamentally informational, then consciousness might play a more central role in the universe than materialistic science has traditionally assumed. Consciousness, after all, is essentially an information processing phenomenon, the universe's way of becoming aware of itself through the emergence of observing systems capable of extracting and integrating information about their environment. This remains highly speculative, with no scientific consensus about whether consciousness requires quantum information processing or whether it can emerge from purely classical computation. However, the informational interpretation of quantum mechanics does suggest possibilities for understanding consciousness that go beyond conventional materialistic frameworks. Some researchers are exploring whether quantum effects in biological systems might contribute to consciousness, cognition, or other aspects of mental function. While these investigations remain preliminary and their results are disputed, they point toward intriguing possibilities for understanding how mind relates to the fundamental information processing activities that occur at the quantum level. The relationship between consciousness and quantum information becomes particularly intriguing when we consider the role of measurement in quantum mechanics. If consciousness is fundamentally about processing information, and if quantum measurement involves the extraction of classical information from quantum systems, then conscious observation might represent a special type of information processing that plays a unique role in the transition from quantum possibilities to classical realities. This doesn't mean that consciousness directly controls quantum events through intention or will. The scientific evidence strongly suggests that individual thoughts or emotions do not directly influence quantum systems in measurable ways. However, The act of conscious observation might participate in the information processing activities that determine which aspects of quantum reality become accessible to classical description. The implications extend beyond individual consciousness to questions about the role of information in the universe as a whole. If quantum mechanics describes how information propagates and transforms throughout the cosmos, then the emergence of conscious observers might represent a fundamental phase transition in the universe's information processing capacity. Before consciousness emerged, the universe processed information through purely physical interactions between quantum systems. With the advent of consciousness, the universe gained the ability to process information about itself, to become self-aware through the activities of observing systems embedded within the larger cosmic information network. This self-awareness might not be limited to biological consciousness as we know it. Some interpretations suggest that any sufficiently complex information processing system might exhibit consciousness-like properties, whether it's based on carbon chemistry, silicon computation, or quantum information processing. As these ideas settle into your awareness, consider how they might influence your understanding of your own place in the cosmic information network. If consciousness represents the universe becoming aware of itself, then your own awareness might be more than just a byproduct of complex chemical processes. It might be a fundamental feature of the universe's information processing activities, a way for the cosmos to experience and understand itself from within. The exploration of quantum consciousness leads us to consider another profound mystery that challenges our understanding of time and causality. In classical physics, events unfold in a clear temporal sequence. Causes precede effects, and the past is fixed while the future remains open to multiple possibilities. But quantum mechanics reveals a more complex relationship between past, present, and future that defies our ordinary temporal intuitions. We've already encountered one example of this temporal strangeness in delayed choice experiments, where decisions made after particles have passed through double slits still determine whether they exhibit wave or particle behavior. But the implications go even deeper, suggesting that the quantum universe might not be organized around a single universal timeline, but rather around more complex temporal structures that allow for mutual influence between events that we would classically consider to be temporally separated. Some interpretations of quantum mechanics propose that quantum events exist in a kind of temporal superposition, where past, present, and future states coexist until measurement forces the system to choose a particular temporal configuration. Just as spatial superposition allows particles to exist in multiple locations simultaneously, temporal superposition might allow events to exist at multiple times simultaneously until observation collapses the temporal wave function into a definite sequence. This temporal flexibility might help explain some of the stranger aspects of quantum entanglement. If entangled particles can maintain instantaneous correlations across space, perhaps they can also maintain correlations across time, with measurements performed at one moment influencing the behavior of the system at other moments in ways that transcend classical causality. The possibility of temporal quantum correlations raises profound questions about the nature of time itself. If quantum events can influence their own past and future states, then time might be more like space than we realize, with past and future being directions rather than absolute categories. Just as we can move backward and forward through space, quantum systems might be able to propagate influences backward and forward through time within certain limits. This doesn't mean that quantum mechanics allows for practical time travel or the violation of macroscopic causality. The temporal correlations, like the spatial correlations in entanglement, operate according to subtle rules that prevent them from creating logical paradoxes or allowing for the transmission of information in ways that would violate the overall causal structure of space-time. But it does suggest that our ordinary experience of time as a flowing river carrying us from past to future might be a simplified picture that emerges at macroscopic scales. At the quantum level, time might be more like a landscape that can be explored in multiple directions, with events connected by correlations that transcend simple temporal sequence. As you contemplate these temporal mysteries, notice how they might relate to your own experience of time and memory. Have you ever had moments where past, present, and future seem to converge in a single instant of awareness, where the boundaries between then and now became fluid and permeable? The quantum universe revealed by these investigations is a place where identity, locality, temporality, and even reality itself become fluid and context-dependent. The solid, predictable world of classical physics gives way to a cosmos where possibilities coexist, where relationships transcend space and time, where observation participates in creation, and where consciousness might play a fundamental role in the universe's information processing activities. This transformation in our understanding of reality has profound implications that extend far beyond physics into philosophy, psychology, and even spirituality. If the universe is fundamentally relational rather than compositional, if consciousness participates in the creation of reality rather than simply observing it, if time and space emerge from more fundamental quantum correlations, then many of our most cherished assumptions about the nature of existence require fundamental reconsideration. The implications ripple through every aspect of human knowledge and experience. The scientific method itself, based on the assumption of objective observation of independent phenomena, must grapple with the discovery that observation and phenomenon are inextricably intertwined. The notion of individual identity, rooted in the assumption that persons exist as separate entities with definite boundaries, encounters the quantum reality where boundaries are fluid and identity emerges from relationships rather than existing independently. Even our understanding of knowledge and truth must evolve to accommodate the quantum insight that reality is participatory rather than simply objective. Truth becomes not something we discover about an independent world, but something we participate in creating through our interactions with the quantum information networks that constitute existence itself. Yet far from being merely destructive of our classical worldview, quantum mechanics opens doorways to new possibilities for understanding ourselves and our place in the cosmic order. If consciousness represents the universe's capacity for self-awareness, then every moment of conscious experience participates in the universe's ongoing project of understanding itself. If reality emerges from relationships rather than existing as fixed facts, then we are not passive observers of a predetermined world, but active participants in an ongoing creative process. If quantum correlations connect all things across space and time, then the boundaries between self and cosmos, between mind and matter, between present and eternity, might be more permeable than we ever imagined. The journey through quantum reality reveals a universe far stranger, more beautiful, and more participatory than our ancestors ever dreamed. It's a cosmos where mystery and knowledge dance together, where scientific discovery leads not to final answers, but to ever deeper questions, where the investigation of matter reveals the fundamental role of mind, and where the exploration of the smallest scales opens vistas of cosmic significance. As we continue this exploration, we'll delve even deeper into the implications of quantum reality for consciousness, creativity, and the ultimate nature of existence itself. We'll examine how quantum principles might relate to meditation, mystical experience, and the cultivation of wisdom. We'll explore what it might mean to live consciously in a quantum universe, and how these scientific discoveries might inform our understanding of ethics, meaning, and the art of being fully human. But for now, let these quantum revelations settle gently into your awareness. Notice how they challenge your assumptions about solidity, separateness, and certainty. As you move through your day, you might find yourself wondering about the quantum dance of possibilities that underlies every apparently solid surface, every moment of apparent certainty, every experience of apparent separation from the world around you. The universe revealed by quantum mechanics is not just stranger than we imagine, it's stranger than we can imagine. Yet it's also more beautiful, more interconnected, and more alive with possibility than the mechanical cosmos of classical physics ever suggested. And you, as a conscious being capable of contemplating these mysteries, are not separate from this quantum reality, but an integral part of its unfolding story. The deepest implications of quantum mechanics emerge when we recognize that these strange phenomena don't occur in some distant microscopic realm separate from our everyday experience. They form the hidden foundation of everything we know and experience, including the very consciousness that contemplates these mysteries. Every thought arising in your mind, every sensation flowing through your awareness, every moment of recognition or understanding emerges from quantum processes that operate according to principles that transcend classical logic. This realization transforms quantum mechanics from an abstract scientific theory into something far more intimate and immediate. The wave functions describing electrons in your brain, the quantum fields permeating the space around and within your body, the entanglement correlations connecting you to the broader cosmos. These aren't distant phenomena to be studied objectively, but the very fabric from which your moment-to-moment experience is woven. Consider the remarkable fact that consciousness itself appears to violate many of the assumptions that classical physics makes about the nature of complex systems. Classical systems, no matter how complicated, can always be understood by breaking them down into simpler components and analysing how those components interact. The behaviour of the whole can, in principle, be predicted from knowledge of the parts. But consciousness exhibits properties that seem to resist this reductionist approach. The unified field of awareness that characterises conscious experience cannot be decomposed into separate components without losing its essential character. Consciousness appears to be fundamentally holistic, exhibiting the kind of non-separable unity that quantum mechanics reveals at the level of entangled systems. This parallel between consciousness and quantum holism has led some researchers to investigate whether quantum effects in biological systems might contribute to the emergence of conscious awareness. While the brain is generally considered too warm and noisy to maintain the delicate quantum coherence required for large-scale quantum effects, some studies suggest that biological systems might have evolved mechanisms to protect and exploit quantum coherence in specific molecular processes. Certain proteins involved in photosynthesis, for example, appear to use quantum superposition to explore multiple energy pathways simultaneously, selecting the most efficient route for transferring energy with a precision that would be impossible using purely classical mechanisms. Some researchers have proposed that similar quantum effects might occur in microtubules within neurons, potentially contributing to the integration of information that characterizes conscious awareness. These investigations remain highly speculative, with no scientific consensus about whether consciousness requires quantum information processing or whether it can emerge from purely classical neural computation. However, the possibility that consciousness and quantum mechanics might be intimately related opens intriguing avenues for understanding both phenomena. If consciousness does involve quantum information processing, it might help explain some of the puzzling features of conscious experience that have resisted classical explanation. The unity of consciousness, its apparent ability to integrate vast amounts of information into coherent experiences, its capacity for creativity and insight, and its relationship to the quantum measurement process might all reflect quantum properties operating at biological scales. But even if consciousness turns out to be a purely classical phenomenon, the quantum mechanical description of reality still has profound implications for how we understand the relationship between mind and cosmos. If the physical world consists of quantum information rather than classical matter, then consciousness, as an information processing phenomenon, might be more fundamental to the universe than materialistic science has traditionally assumed. As you reflect on these possibilities, consider how they might influence your understanding of the relationship between your inner experience and the physical world around you. If consciousness and quantum mechanics both reveal non-local, holistic properties that transcend classical boundaries, what might this suggest about the nature of your own awareness and its connection to the broader universe? The exploration of consciousness and quantum mechanics leads naturally to questions about the role of observation and intention in quantum systems. While the scientific evidence clearly shows that individual thoughts or emotions do not directly control quantum events in measurable ways, the role of conscious observation in quantum measurement remains one of the most profound, unsolved problems in physics. Some interpretations suggest that consciousness plays a special role in collapsing wave functions precisely because conscious observation involves the extraction and integration of information in ways that differ qualitatively from purely physical measurement processes. According to this view, consciousness doesn't control quantum events through will or intention, but it does participate in the information processing activities that determine which aspects of quantum reality become accessible to classical description. This subtle but important distinction helps clarify the relationship between consciousness and quantum mechanics, while avoiding the common misconception that quantum physics supports the idea that thoughts directly create reality. The scientific evidence strongly suggests that individual mental states do not directly influence quantum systems in ways that could be used to manifest desired outcomes or control external events. However, the participatory nature of quantum reality does suggest that consciousness plays a more active role in the universe than purely materialistic worldviews would suggest. If reality emerges through relationships and interactions rather than existing as fixed facts independent of observation, then conscious beings are not passive observers of a predetermined world, but active participants in an ongoing creative process. This participatory view of reality has profound implications for how we understand knowledge, ethics, and the meaning of human existence. If our observations and interactions participate in shaping the nature of reality, then we bear a kind of cosmic responsibility for the quality of attention we bring to our experience and our relationships with others and with the natural world. The cultivation of mindful awareness, the practice of ethical action, the pursuit of wisdom and understanding. These activities take on new significance when viewed from the perspective of a participatory universe. They become not just personal practices aimed at individual well-being, but ways of participating constructively in the universe's ongoing process of self-creation and self-understanding. This doesn't mean that consciousness has unlimited power to shape reality according to desire or will. The quantum universe operates according to precise mathematical laws that constrain the ways in which observation and reality interact. But it does suggest that the quality of consciousness we bring to our experience might have subtle but significant effects on the ways in which quantum possibilities crystallize into classical actualities. Some contemplative traditions have long recognized that the quality of awareness influences the quality of experience in ways that transcend simple psychological causation. Meditation practices, for example, are often described as revealing the participatory nature of perception, showing how the act of observing with different qualities of attention can reveal different aspects of reality. While these contemplative insights remain largely outside the scope of current scientific investigation, they resonate intriguingly with the participatory picture of reality revealed by quantum mechanics. Both suggest that the relationship between observer and observed is more intimate and creative than classical science assumed, and both point toward possibilities for understanding consciousness that go beyond purely mechanistic frameworks. As you contemplate these ideas, notice how they might influence your own practice of attention and awareness. If the quality of consciousness you bring to each moment participates in subtle ways in the unfolding of reality, what responsibility might this create for the cultivation of wisdom, compassion, and skillful action? The implications of quantum mechanics for human consciousness and behavior extend beyond individual awareness into questions about collective consciousness and social reality. If individual minds are composed of quantum information processing systems that maintain non-local correlations with their environment, then the boundaries between individual consciousness might be more permeable than we typically assume. Some researchers have investigated whether groups of people might exhibit collective quantum effects, such as synchronized brain activity or coordinated behavioral responses that cannot be explained by classical communication or social influence. While these studies remain controversial and their results are disputed, they point toward possibilities for understanding collective consciousness that go beyond conventional psychological and sociological frameworks. The idea that consciousness might have quantum properties that allow for non-local correlations between individuals remains highly speculative, with no scientific consensus about whether such effects exist or could be detected experimentally. However, the quantum mechanical insight that reality emerges through relationships rather than existing independently does suggest new ways of understanding the social and cultural dimensions of human experience. If consciousness participates in the creation of reality through the quality of attention and intention it brings to experience, then collective practices aimed at cultivating wisdom, compassion, and ethical action might have effects that extend beyond their immediate social and psychological consequences. Meditation groups, prayer circles, and other contemplative practices might participate in subtle ways in the universe's information processing activities, contributing to the emergence of more harmonious and creative patterns in the collective human experience. Again, this remains speculative, with no proven scientific mechanism by which collective consciousness could influence external events through quantum correlations. However, the participatory nature of quantum reality does suggest that the cultivation of wisdom and ethical action might have cosmic significance beyond their obvious benefits for individual and social well-being. The transformation in worldview brought about by quantum mechanics extends beyond questions of consciousness and measurement into fundamental issues about the nature of knowledge, truth, and reality itself. If the universe is fundamentally relational rather than compositional, if properties emerge through interaction rather than existing independently, if consciousness participates in the creation of reality rather than simply observing it, then many of our most basic philosophical assumptions require fundamental reconsideration. The classical notion of objective truth, based on the assumption that reality exists independently of observation and can be described accurately through careful measurement and logical analysis, encounters the quantum insight that observation and reality are inextricably intertwined. Truth becomes not something we discover about an independent world, but something we participate in creating through our interactions with the quantum information networks that constitute existence. This doesn't lead to relativism or the abandonment of scientific rigor. Quantum mechanics is one of the most precisely tested theories in the history of science, with predictions confirmed to extraordinary accuracy in countless experiments. The mathematics of quantum mechanics provide extraordinarily precise predictions about the probabilities of different measurement outcomes, even while revealing that individual quantum events remain fundamentally unpredictable. This precision within uncertainty suggests a more nuanced relationship between knowledge and reality than either classical objectivity or postmodern relativism would suggest. Quantum mechanics reveals that the universe is neither completely determined nor completely arbitrary, but operates according to principles that allow for both lawful structure and creative novelty. The implications ripple through every domain of human inquiry. In physics, the recognition that observation participates in the determination of reality has led to new interpretations of quantum mechanics that emphasize information and relationship over substance and independence. In philosophy, the quantum insights challenge traditional distinctions between subject and object, mind and matter, observer and observed. In psychology, the possibility that consciousness involves quantum information processing opens new avenues for understanding creativity, insight, and the integration of experience. In contemplative practice, the participatory nature of quantum reality resonates with ancient insights about the intimate relationship between awareness and the phenomena that arise within it. As these implications continue to unfold across different fields of human knowledge, we begin to see the emergence of a more integrated worldview that honors both the precision of scientific inquiry and the mystery of conscious experience. This worldview doesn't abandon rationality or empirical investigation, but recognizes that these powerful tools operate within a larger context of participatory relationship between knower and known. The universe revealed by quantum mechanics is not a collection of separate objects governed by mechanical laws, but a vast web of relationships and correlations that give rise to the appearance of separate objects through the very act of observation. This web extends across all scales of reality, from the quantum fluctuations of empty space to the neural networks of conscious brains to the social and cultural patterns that shape human civilization. Within this web, consciousness emerges not as an accidental byproduct of complex chemical processes, but as a fundamental feature of the universe's information processing activities. Through consciousness, the universe becomes capable of observing itself, of recognizing the patterns and relationships that constitute its own structure, of participating consciously in its own ongoing evolution. This recognition transforms our understanding of what it means to be human in a quantum universe. We are not separate observers of an independent reality, but integral participants in the cosmic process of self-awareness and self-creation. Every moment of conscious experience, every act of attention and recognition, every choice we make about how to respond to the circumstances of our lives participates in the universe's ongoing project of understanding and expressing itself. The cultivation of wisdom, compassion, and ethical action takes on cosmic significance from this perspective. These are not merely personal virtues aimed at individual well-being, but ways of participating constructively in the universe's information processing activities, contributing to the emergence of greater coherence, creativity, and consciousness in the cosmic web of relationships. This doesn't mean that individual actions have unlimited power to shape reality according to personal desires. The quantum universe operates according to precise mathematical constraints that limit the ways in which observation and intention can influence outcomes. But it does suggest that the quality of consciousness we bring to each moment has subtle but significant effects on the patterns that emerge in our immediate experience and our relationships with others. The practice of mindful awareness, for example, might be understood not just as a technique for reducing stress or enhancing well-being, but as a way of participating more skillfully in the universe's information processing activities. When we observe our thoughts and emotions with clear, non-judgmental attention, we might be contributing to the emergence of greater coherence and integration in the quantum information networks that constitute our experience. Similarly, the cultivation of compassion and ethical action might have effects that extend beyond their obvious benefits for social harmony and individual fulfillment. By attending to the welfare of others and the health of the natural world, we might be participating in the universe's movement toward greater complexity, consciousness, and creativity. These possibilities remain speculative, with no proven scientific mechanism by which individual consciousness could influence external events through quantum correlations. However, the participatory nature of quantum reality does suggest that contemplative practice and ethical action might have significance that extends beyond their immediate psychological and social effects. As you reflect on these ideas, consider how they might influence your own approach to daily life and spiritual practice. If consciousness participates in subtle ways in the unfolding of reality, what qualities of attention and intention might you want to cultivate? How might you participate more consciously in the universe's ongoing process of self-awareness and creative evolution? The exploration of quantum consciousness leads us naturally to consider the relationship between scientific understanding and contemplative wisdom. Throughout human history, contemplative traditions have developed sophisticated methods for investigating the nature of consciousness and reality through direct experience rather than external observation. These traditions have often arrived at insights that resonate remarkably with the discoveries of quantum physics. The recognition that reality is fundamentally relational rather than substantial, that consciousness and phenomena arise interdependently, that the boundaries between observer and observed are more fluid than they appear. These insights appear in various forms across many contemplative traditions. While we must be careful not to conflate ancient wisdom with modern physics, the convergence is striking and suggests possibilities for dialogue between scientific and contemplative approaches to understanding consciousness and reality. Neither approach alone may be sufficient to fully comprehend the mystery of existence, but together they might offer complementary perspectives that enrich our understanding of both domains. Scientific investigation excels at revealing the mathematical structures and causal relationships that govern physical phenomena, providing precise predictions about the behavior of quantum systems and the evolution of complex networks. Contemplative investigation excels at revealing the experiential structures of consciousness itself, providing insights into the nature of awareness, the process of perception, and the relationship between mind and phenomena. The integration of these approaches might lead to new forms of inquiry that combine the rigor of scientific method with the experiential precision of contemplative practice. Some researchers are already exploring whether meditation and other contemplative practices might enhance scientific creativity and insight, while contemplative practitioners are increasingly interested in how scientific discoveries might inform their understanding of the nature of mind and reality. This integration doesn't require abandoning the methodological constraints that make science reliable or the experiential precision that makes contemplative practice transformative. Instead, it suggests possibilities for expanding the scope of human inquiry to include both external observation and internal exploration, both mathematical modeling and direct experience, both analytical understanding and intuitive insight. The quantum universe revealed by modern physics is vast enough to accommodate both approaches, mysterious enough to require multiple perspectives, and participatory enough to benefit from the conscious engagement of both scientific and contemplative intelligence. As we move deeper into the 21st century, the dialogue between science and contemplative wisdom is likely to become increasingly important for addressing the challenges facing human civilization. Climate change, social inequality, technological disruption, and the search for meaning in an increasingly complex world all require forms of intelligence that transcend the boundaries between analytical and intuitive knowing. The quantum mechanical insight that reality emerges through relationship and interaction suggests that these challenges might be most effectively addressed through collaborative approaches that honor both the precision of scientific analysis and the wisdom of contemplative understanding. Neither approach alone may be sufficient to navigate the complexity of our current situation, but together they might offer resources for responding more skillfully to the opportunities and difficulties of our time. Take a moment to consider how these integrative possibilities might appear in your own life. Are there ways in which analytical understanding and experiential insight might complement each other in your approach to personal challenges or creative projects? How might you cultivate both scientific curiosity and contemplative awareness in your engagement with the world around you? The implications of quantum mechanics for human consciousness and collective wisdom extend into questions about the evolution of consciousness itself. If consciousness represents the universe's capacity for self-awareness, then the emergence and development of consciousness might be understood as a fundamental feature of cosmic evolution rather than an accidental byproduct of biological complexity. From this perspective, the evolution of human consciousness from simple awareness to complex self-reflection, from individual intelligence to collective wisdom, from local concerns to cosmic perspective, might represent stages in the universe's ongoing project of understanding itself through the emergence of conscious observers capable of increasingly sophisticated forms of inquiry and insight. The development of scientific method, the cultivation of contemplative wisdom, the emergence of global communication networks, and the growing recognition of our interconnectedness with the natural world might all be understood as aspects of this cosmic evolution of consciousness. This doesn't mean that consciousness evolution is predetermined or that it will inevitably lead to particular outcomes. The quantum universe is characterized by genuine creativity and novelty, with new possibilities emerging through the interaction of existing patterns rather than being determined by past conditions alone. But it does suggest that the choices we make about how to develop and apply human consciousness might have significance that extends beyond their immediate practical consequences. The cultivation of wisdom, creativity, and ethical sensitivity might be understood as contributions to the universe's evolving capacity for self-awareness and self-direction. The technologies we develop, the social institutions we create, the forms of education we provide, the contemplative practices we cultivate, all participate in shaping the future evolution of consciousness and its capacity to participate constructively in the cosmic process of creative development. From this perspective, the current moment in human history takes on particular significance. We are living at a time when human consciousness is powerful enough to influence the evolution of life on Earth, yet still developing the wisdom necessary to exercise this influence skillfully. The quantum mechanical insight that observation participates in the creation of reality suggests that the quality of consciousness we bring to this historical moment might play a crucial role in determining which possibilities emerge from the current situation. This is not a matter of individual thoughts directly controlling external events, but of collective human consciousness participating in the information processing activities that shape the evolution of complex systems. The cultivation of individual wisdom and compassion, the development of more skillful forms of social organization, the creation of technologies that enhance rather than diminish human flourishing, the protection and restoration of natural ecosystems, all contribute to the emergence of more coherent and creative patterns in the global network of relationships that constitute our planetary civilization. As you contemplate these possibilities, consider how your own consciousness development might contribute to this larger evolutionary process. What qualities of awareness and action might you want to cultivate? How might you participate more consciously in the collective project of developing human wisdom and creating conditions that support the flourishing of life on Earth? The journey through quantum reality ultimately leads us to a profound recognition. The universe is not a machine we observe from the outside, but a creative process we participate in from within. Consciousness is not separate from the physical world, but represents the universe's capacity to know itself through the emergence of aware beings capable of recognition, understanding, and creative response. This recognition transforms our understanding of science, spirituality, and the meaning of human existence. Science becomes not just a method for predicting and controlling natural phenomena, but a way of participating consciously in the universe's ongoing project of self-understanding. Spirituality becomes not an escape from the physical world, but a deepening engagement with the creative mystery that manifests as both consciousness and cosmos. The meaning of human existence emerges not from our separation from the natural world, but from our capacity to serve as conscious participants in the universe's evolution toward greater complexity, creativity, and awareness. We are the universe becoming aware of itself, developing the capacity to respond consciously to the challenges and opportunities that arise in the course of cosmic evolution. The quantum mechanical revelation that reality emerges through relationship and interaction suggests that this participation is not optional but fundamental to our nature as conscious beings. Every moment of awareness, every act of understanding, every choice we make about how to respond to the circumstances of our lives contributes to the patterns that emerge in the cosmic web of relationships. This participatory understanding doesn't diminish the importance of scientific rigor or contemplative precision, but places them within a larger context of creative engagement with the mystery of existence. Both analytical investigation and experiential exploration become ways of participating more fully in the universe's ongoing process of self-discovery and creative expression. The implications extend through every aspect of human life and culture. Education becomes not just a transmission of information, but the cultivation of consciousness, capable of participating wisely in cosmic evolution. Technology becomes not just the manipulation of natural forces, but the extension of human consciousness in ways that enhance rather than diminish the creative potential of the universe. Art becomes not just personal expression, but a way of revealing and celebrating the creative mystery that manifests as both consciousness and cosmos. Ethics becomes not just social convention, but participation in the universe's movement toward greater coherence, complexity, and compassion. As these quantum insights continue to permeate human culture, they may contribute to the emergence of new forms of wisdom that integrate scientific precision with contemplative depth, analytical rigor with experiential insight, technological capability with ecological sensitivity. The universe revealed by quantum mechanics is vast enough to encompass both the mathematical elegance of physical law and the experiential richness of conscious awareness. Mysterious enough to inspire both scientific investigation and contemplative inquiry, participatory enough to invite both analytical understanding and creative engagement. We stand at a remarkable moment in the evolution of human consciousness, with access to both the precision of modern science and the wisdom of contemplative traditions, both global communication technologies and growing awareness of our interconnectedness with all life. The choices we make about how to integrate and apply these resources may play a crucial role in shaping the future evolution of consciousness on Earth and beyond. The quantum universe invites us to participate consciously in this evolutionary process, not as separate observers trying to control external events, but as integral participants in the cosmic web of relationships that gives rise to both consciousness and phenomena. Through the cultivation of wisdom, creativity, and ethical sensitivity, we can contribute to the emergence of more coherent and compassionate patterns in the global network of consciousness that is gradually awakening to its own nature and possibilities. As you continue to explore these ideas in your own life and practice, remember that you are not separate from the quantum reality we've been investigating. You are quantum reality becoming conscious of itself, developing the capacity to participate more skillfully in the creative evolution of consciousness and cosmos. The wave functions describing the particles in your brain, the quantum fields permeating the space around your body, the entanglement correlations connecting you to the broader universe. These are not abstract phenomena to be studied from a distance, but the intimate fabric of your own being and awareness. Every breath you take, every thought that arises, every moment of recognition or understanding emerges from quantum processes that operate according to principles that transcend classical logic, yet give rise to the coherent patterns of your conscious experience. This recognition transforms the exploration of quantum mechanics from an intellectual exercise into a form of self-discovery, a way of recognizing your own deeper nature as a conscious expression of the creative mystery that manifests as the universe itself. The journey into quantum reality reveals not just the strange behavior of subatomic particles, but the participatory nature of consciousness and its intimate relationship with the creative processes that govern the evolution of the cosmos. In recognizing this relationship, we discover both the profound responsibility and the extraordinary opportunity that comes with conscious participation in the universe's ongoing project of self-understanding and creative expression. The quantum universe is not just stranger than we imagine, it's more beautiful, more creative, and more alive with possibility than the mechanical cosmos of classical physics ever suggested. And you, as a conscious being capable of contemplating these mysteries, are not separate from this quantum reality, but an integral part of its unfolding story, a unique expression of the universe's infinite creativity and its endless capacity for self-discovery and transformation. As you drift off to sleep tonight, or continue with your day, carry with you this recognition that you're not just in the universe, but the universe is in you, expressing itself as your awareness, your creativity, your capacity for love and understanding. The quantum dance of possibilities that underlies all existence is the same dance that gives rise to every moment of your conscious experience. Every insight that arises, every choice you make about how to participate in the creative evolution of consciousness and cosmos. The exploration of quantum reality ultimately returns us to the most intimate mystery of all, the nature of our own awareness and its relationship to the creative source from which all possibilities arise. In recognizing this relationship, we discover that the investigation of the quantum world is not separate from the cultivation of wisdom and compassion, but represents another pathway into the heart of the mystery that we ourselves are. If you found yourself moved by these quantum revelations about the nature of reality and consciousness, you might be drawn to explore how these same principles manifest in your direct experience. The mysterious connections we've discovered between observation and reality, between consciousness and cosmos, suggest possibilities for understanding your own awareness that go far beyond what classical science ever imagined possible. In our exploration of the quantum connection between your mind and the universe, and why you can feel it, we'll journey into the experiential dimensions of these quantum insights, investigating how the participatory nature of quantum reality might be directly accessible through the cultivation of refined awareness and contemplative insight. The universe doesn't just exist around you, it exists through you. Right now, as you absorb these words, quantum fields are processing information through the neural networks of your brain in ways that make your very thoughts possible. The boundary between your consciousness and the quantum realm isn't a wall to be crossed, but a threshold that dissolves the moment you look closely enough to see it. Welcome to an exploration of how quantum physics reveals something profound about the nature of reality itself, something that changes not just what we know about the world, but how we experience being alive within it. I'm here to guide you through discoveries that have shattered our most basic assumptions about existence, discoveries that reveal a universe far more participatory, far more alive, and far more mysterious than we ever imagined. Tonight we'll journey through the looking glass of modern physics, where solid matter dissolves into probability waves, where the act of observation shapes reality itself, and where the deepest insights of science converge with the most profound questions about consciousness and meaning. This isn't just an intellectual exercise. By the time we finish this exploration together, you may find that your relationship to existence itself has shifted in subtle but profound ways. So settle in, allow your breathing to deepen, and prepare to discover how quantum mechanics doesn't just describe distant particles in laboratories, but illuminates the very nature of awareness, reality, and your place in the cosmic dance of existence. In the quiet moments just before sleep, when your mind begins to release its grip on the familiar categories that organize daily experience, you might occasionally glimpse something that has puzzled human beings for millennia. The boundaries between inner and outer, between self and world, between observer and observed, seem to soften and become permeable. What science is now discovering is that these liminal experiences might offer more than poetic insight. They might be revealing something fundamental about the nature of reality itself. For centuries, the scientific worldview rested on what seems like an unshakable foundation: the assumption that consciousness and the physical world operate according to entirely different principles. Mind was subjective, personal, ephemeral. Matter was objective, universal, enduring. The observer stood apart from the observed, studying a world that existed independently of whether anyone was looking at it. But quantum mechanics has revealed cracks in this foundation, cracks that grow wider the more closely we examine them. The quantum world operates according to principles that seem to bridge the classical divide between consciousness and matter, between subjective experience and objective reality, between the observer and the observed. Consider what happens when you turn your attention inward and observe your own thoughts. The very act of observing seems to change the nature of what you're observing. Thoughts that were flowing freely suddenly become more defined, more stable, more amenable to examination. It's as if consciousness, when it observes itself, participates in determining the nature of what it finds. This participatory relationship between observation and reality, so familiar in the realm of introspection, turns out to be a fundamental feature of the quantum world as well. Particles don't simply possess definite properties waiting to be discovered by measurement. Instead, the act of measurement participates in determining which properties manifest from the quantum realm of pure possibility. As we come to the end of this journey through the quantum realm, take a moment to notice how these ideas might be settling into your awareness. The world around you hasn't changed, yet perhaps your relationship to it has shifted in subtle ways. The solid surfaces that once seemed so permanent now whisper of probability waves and quantum possibilities. The space between your thoughts now hints at the same mysterious emptiness that gives rise to virtual particles dancing in the cosmic void. We've travelled together through territories where common sense dissolves and deeper truths emerge, where the act of observation participates in the creation of reality itself, and where the boundaries between consciousness and cosmos become beautifully, mysteriously permeable. While these discoveries challenge everything we thought we knew about existence, they also invite us into a more participatory, more alive, more interconnected understanding of what it means to be conscious beings in a quantum universe. The implications ripple far beyond physics laboratories into every moment of your lived experience. You are not separate from the quantum dance we've explored tonight, but an integral expression of it, a unique way the universe has found to know itself from within. As you continue through your days, you might find yourself wondering about the hidden quantum connections linking you to everything around you, the observer effect your consciousness creates, and the profound mystery of awareness itself unfolding through the fabric of space and time.